The following formula finds the radial area of a region defined using polar coordinates. So what I mean by that is if you had a polar function like r equals cosine theta, and you go to graph r equals cosine theta. Well, when theta is equal to 0, cosine is 1. When theta gets around to how would this graph look? When cosine of pi over 2 is 0, right? So it would look like going from 1 to 0, and then, oh yeah, that would just be a circle. It's kind of a boring function. Let's do something else. Let's do cosine of theta plus 1 and see what that would look like. So then we start at the point 2, and then as theta goes to pi over 2, this function would go just to 1. And then as theta goes to pi, cosine would go to -1, so this thing would go to 0. And then it starts to come back from -1 at theta equals 3 pi over 2. Cosine would be back to 0, so we're back to 1. And then when cosine gets back to, when theta gets back to 2 pi, it should be back here. That's a slightly more exciting graph. Let me see how close we got. We can say r equals cosine theta plus 1. Let's see what it looks like. Okay, so that's how it's supposed to look. What I mean by radial area is for any given two values of theta, like theta A and I'll color code this theta B. Let's say this angle is theta B, and this other angle represents theta A. I could draw rays that emanate from the origin directly out in the direction of theta A and theta B. And then suppose we shade in the region in between those. So it's bounded by my polar curve in blue, and it's also bounded by these rays that come out of the origin radially at those angles. Well, now I guess I should have just used the same notation I use here because I use alpha to be the lower bound. And so instead of theta A, let's call this alpha as the lower bound angle. And then the upper bound angle is going to be beta, according to the way I typed out this formula. So let's this green angle here be beta. Well, the way I would calculate the shaded blue region, the radial area, is with this integral. The area is equal to 1/2 integral from alpha to beta of r squared d theta. And if you're looking for an explanation for why this integral could possibly tell you what the area is enclosed radially in a polar curve, because what we're basically doing is adding up not rectangles this time. It's not like a Riemann sum where we add up the little rectangles, but it's kind of like the Riemann sum where we add up sectors of a circle, and it's not all the same circle, but they're different circles where the radius of the circle is the distance from the origin to the polar curve. So where the radius is a function of theta, we calculate the area of each one of these little circle sectors, and then you add them up, and you get a certain sum that's kind of like a Riemann sum. Maybe it's a good approximation, maybe it's not so good. But as we get more and more and more sectors, we break down our area into smaller little bite-sized chunks. It gets to be a better approximation, and then the limit as n approaches infinity and we get more and more and more sectors in there, the relative error goes to 0. And we get the area we're looking for, the radial area. The area of one of these sectors, by the way, would be, we'll call it delta A for the area of one sector. That would kind of be like the area of the total circle divided by 2 pi, because there's 2 pi radians in a circle, times whatever that delta theta is, times whatever angle this sector encloses. So we take the full area of the entire circle, and then we multiply it by what fraction of the angular measure is enclosed by the sector. So that would be delta theta, which is this angle here, delta theta, divided by 2 pi. So there's 2 pi total radians to make a full revolution. So then the pi's cancel, because there's a pi in the numerator, a pi in the denominator, and I get 1/2 r squared delta theta as the area of one sector. But we're not just taking the area of one sector. I want the area that I get from summing up all of the sectors. So we take a sum of things that look like 1/2 r squared delta theta, and then in the limit process, as n approaches infinity and delta theta approaches 0, we get the integral, which is the total area. And on the right side, the integral of r squared d theta. We use a lowercase d to represent a change in theta that goes to 0. And the 1/2 is just a constant, so we can also write that outside the integral. We've got to have some starting point, some ending point, and there we go. That's our formula. So find the radial area enclosed by the polar curve on the interval from 0 to theta to 2 pi. In other words, I wonder if Desmos can do an inequality with polar coordinates, like r equals theta looks like this, but what would the area look like enclosed radially? That'd be r less than or equal to theta from 0 to 2 pi. Okay, perfect. That's what I want. So we're trying to find this blue shaded region. And to do this, we're going to use that area formula, which is 1/2 integral from alpha to beta of r squared d theta. And in this particular case, that's going to be 1/2 integral, what's my lower bound and upper bound? 0 and 2 pi. And if my curve is described by r equals theta, then how should I write my integrand? as is theta squared. So the antiderivative of theta squared with respect to theta is
1/3 theta cubed.
Mm-hmm. When I plug in 2 pi, I get 8 pi cubed. When I plug in 0, I get 0. So my answer is that this shaded blue region in the plane is 4/3 pi cubed. Pi cubed would be about 30. So 4/3 of 30 would be like 40. Does that look like an area of 40 to you? I mean, maybe. They're like 16 plus 8. It could be. Okay, questions? No? Find the radial area enclosed by the polar curve shown here. So r equals 2 cosine of 2 theta. It makes that nice shape. I'm a little bit wary of starting this problem because I know that cosine has positive values, but cosine also has negative values on some intervals. And so if I integrate negative values, I don't want it to like be subtracting from my area. But then you know what? The other thing I think is in the area formula for the polar curve, the integrand's squared anyways. Yeah, so I don't need to worry about that. So we write down our formula. 1/2 integral from alpha to beta of r squared d theta. And this time r is cosine of 2 theta. So we call that cosine squared of 2 theta. And I wonder what my what do you call it? Lower bound and upper bound are. The lower bound and the upper bound of the integral are going to be in terms of my angle theta, since you see the d theta at the end of the integral. And so think about the angle we make with the positive x-axis as theta goes around here from 0 to 2 pi. I think the way that this curve gets traced out is like starting here when theta is 0, it goes along this route, because along this point where I'm currently drawing the arrows, r is actually negative. So this is negative values of cosine. And so Then we get positive values of cosine again, and theta is pointing us into quadrant 2. And then right here we get negative values of cosine when we pass through the origin again. So theta is actually pointing in quadrant 3, but the negative r values are putting us in quadrant 1. And then when I pass through the origin again, I get positive r values, and theta is putting us in the 4th quadrant. And then we're back. So I think that the lower bound of theta is 0 and the upper bound is 2 pi. Again, just like before. Does that make sense? So one thing I like to do on Desmos is change this to a variable like a, and then say a is equal to 1 or whatever. And you can set a to go from 0 to 2 pi. Because if you set up Desmos just like this, you can see how Desmos draws it. You just drag the slider around, and here's theta equals 0. And as theta is increasing from 0 to 2 pi, it looks like this. And the only reason I know how to trace these curves myself is because I've done this with Desmos like 10 or 15 times. So Desmos makes you smarter. And then once we get our lower bound and upper bound figured out, we have to take an antiderivative of cosine squared. How do I take the antiderivative of cosine squared? Do you know? Give you a hint. There's a power reduction identity for cosine squared, and it goes like cosine squared x is equal to
1/2 1 plus cosine.
1/2 1 plus cosine 2 theta, or 2x in this case. And so I don't just have cosine of x, I have cosine of 2 theta. And so that 2 theta is actually going to become a 4 theta when I apply that power reduction identity. So area is 1/2 integral from 0 to 2 pi of 1/2 1 plus cosine 4 theta d theta. And so we bring out the 1/2 and I get a quarter. And I can separate this integral where the plus sign is, because of the whole integral additivity stuff, which means the antiderivative of 1 is just theta, where we plug in the upper bound 2 pi and 0. And then the second integral is going to be 1/4 integral from 0 to 2 pi of cosine 4 theta d theta. The antiderivative of cosine is just sine, but I also have to divide by 4 for the sine because of the whole derivative chain rule. And so that's going to be 2 pi divided by 4 is pi half, plus 1 over 16 sine of 4 theta evaluated at 2 pi and at 0. By the way, what is sine of 8 pi?
Is it 0?
Mm-hmm. Yeah, sine of any integer value of pi, any integer multiple of pi is 0. So that last term is going to be 0 minus 0. In other words, the area is pi over 2. And this immediately sounds kind of suspicious to me, I think, because pi over 2 is only like an area of like 1.4. I don't know, maybe that's right. I'm just too suspicious of these things. Like, I always feel like I have to check my answer. Like, what's the integral of 0 to 2 pi cosine squared of 2x? That's pi, and then you divide by 2. Yeah, okay, I guess we got it right. It's pi divided by 2. Nice. Questions? Okay. Convert the following polar curve into a parametric curve. We did this before. We did this before on like the first week of class. So if this sounds familiar, it's supposed to sound familiar. The trick is x is equal to r times cosine theta. Because if we have an xy plane like this, here is a line segment with length r making an angle of theta with the positive x-axis, and I can go ahead and draw a vertical line to complete a right triangle here with the x-axis as my base, and then just the definition of the cosine trig function would say that cosine of theta is the ratio of the adjacent side x divided by the hypotenuse r. And likewise, the definition of sine theta is the ratio of the opposite side y divided by the hypotenuse r. And so multiplying both sides of those equations by r, we get that x is equal to r cosine theta and y is equal to r sine theta. Well, here's my formula for r. And so I get that x is equal to 2 sine theta cosine theta. And y would be equal to 2 sine squared theta. And then all you do to write a parametric curve is you give the x and the y coordinates as a function of some parameter. So just let theta be our parameter. And now you have a parametric curve that does the same thing. And the way you would check your answer here is you go back to Desmos and you say r equals 2 sine theta. And then the parametric curve was 2 sine theta cosine theta, comma 2 sine squared theta. Oops. I need parentheses around my argument. Oh, it's because they're thetas. I need them to be t's so that Desmos will graph my parametric curve. And there we go. If I let t go up to 2 pi, I'm sure it'll work. Yeah, cool. So same circle, correct answer. Questions? You remember that from before? So I can convert any polar curve into a parametric curve that way, just by writing x equals r cosine theta and y equals r sine theta, and then changing the theta to t's. And then I get this. What if I have a curve defined with polar variables, and I want to find the length of that curve? Well, we already derived a formula for the length of a parametric curve. And if I had a parametric curve, the way we found the length is we had an integral from a to b, and by the way, a and b were supposed to be the lower bound and upper bound of my parameter t. So we had an integral from a to b, and the integrand looked like the square root of dx dt squared plus dy dt squared. And we integrate with respect to t. And so I think it was last time we met on Monday, we derived this formula. We drew a picture with the Pythagorean theorem, and we explained how, it's kind of like approximating a curve with a bunch of tiny line segments. And each line segment was the hypotenuse of a right triangle, and that's why we ended up with the integrand that we have. What we're going to do now is use those definitions that are x equals r cosine theta and y equals r sine theta, and we're going to equate my parameter t with the angle we make from the positive x-axis, so we can replace the t's with thetas if we want to, and then we'll see what happens to this formula. First of all, I've got the dx dt. Dx dt is going to be the derivative with respect to t of r cosine theta. Or I should say r cosine t, since we can use theta and t interchangeably. And so the derivative product rule says, first we want the derivative of the first factor, dr dt, times the second factor, cosine of t, plus the first factor, r, times the derivative of the second factor, which is negative sine of t. So that's my derivative according to the product rule. And we think, well, what would happen if I now need dx dt squared, like I have in the integrand? Well, so then we have to take this expression with two terms and then square it. And squaring an expression with two terms means you like FOIL it, you get this first term times itself. So we have dr dt squared times cosine squared. And then we have the last term squared, which would be r squared times negative sine squared, and the negative goes away. And then we get the terms from multiplying the first term by the second term, and we get two of them, right? Because it's first outer and inner. So we get two terms that look like dr dt times r times cosine times negative sine. So I'm going to write minus 2 r cosine t sine t dr dt. Then we do the same thing with y. That is, we're going to take dy dt, which is the derivative with respect to t of r sine theta, or r sine t. And we have to use the derivative product rule to find dr dt. Sine of t plus r times cosine t. And then we take dy dt squared, which means squaring this expression with two terms. And so we take the first term squared plus the second term squared plus 2 times what we get if we multiply them. And together, the first term squared is going to be dr dt squared times sine squared. The second term squared is going to be r squared cosine squared t. And then what I get when I multiply the two terms, and I have to do that twice, so I get 2r dr dt cosine t sine t. And when we're done with that, we can go return to my integral. It might not be a big enough radicand. So what I'm about to write in the radicand is dx dt squared plus dy dt squared. And whenever I add dx dt squared to dy dt squared in the green plus the blue, do you see anything that's going to cancel or simplify? Yeah. This term in green is going to cancel with this term in blue when I add them together, because they are equal and opposite, so they're going to cancel each other out. And you know what else I'm going to try to convince you of, because I'm a little bit lazy and this could save time. What is cosine squared plus sine squared? 1. So anywhere I see cosine squared plus sine squared, I could just replace it with a 1. And what we're about to do is we're about to add the green part plus the blue part. So here I've got cosine squared times dr dt squared plus sine squared times dr dt squared. In other words, I could add these two terms together, I could factor out dr dt squared, and then when I'm left with cosine squared plus sine squared, that's just a 1. So I get dr dt squared. And that comes from this term and that term. Now all that's left are the terms I'm about to shade in green, which is r squared sine squared t and r squared cosine squared t. So how are those going to simplify when I add them together?
Just as r squared.
It'll just be r squared. So you add those terms together, you factor out the r squared, and you're left with cosine squared plus sine squared, and that is just 1. And so the terms I shaded in green become the plus r squared. I guess I was wrong. I didn't need that much space. And this is exactly the formula we're trying to find, right? If I just now go back and replace A with alpha, the starting angle, and B with beta, the ending angle, and then we replace T's with thetas, like I said, we were going to equate T and theta together, then I get exactly the formula I was looking for the length of a polar curve. So you could, if you wanted to, you could always take a polar curve and rewrite it as a parametric curve and then use the parametric curve formula on it. Not have to remember this. But if you do remember this formula, then it's a little bit faster. It's a little bit easier because polar curves are only useful to the extent that you can write a parametric curve in a more compact way. And so it prevents you from doing a lot of messy work if you just go straight for the polar definition. What is the length of the following polar curve where theta goes from negative pi to 0? I'm interested in seeing what this looks like. So r equals e to the negative theta. And we're supposed to let theta go from negative pi to 0. So we're actually looking at this part of the curve. How long is that blue curve? All right. So our formula for length that we just found is integral from alpha to beta of square roots r squared plus dr d theta squared d theta. And when we have the r squared, we're going to replace that with e to the negative 2 theta. What is dr d theta? Very good. So if I had dr d theta squared, what would that be? Awesome. Yep, the negatives go away when we square it. And you gotta use your properties of exponents here. And then plugging that in, we'll see what it looks like. My lower bound's negative pi, my upper bound's 0. Square root of e to the negative 2 theta plus e to the negative 2 theta d theta. So that will be the integral from negative pi to 0 of the square root of 2 e to the negative 2 theta d theta. And that's going to be the square root of 2 times the integral of negative pi to the 0 of what? How do I simplify that?
E to the negative theta.
Awesome. Yep. Since e to the negative 2 theta is the same thing as e to the negative theta squared, then we can just take the square root by writing e to the negative theta. The antiderivative of e to the negative theta is negative e to the negative theta. So you can't forget to pick up a minus sign there when we take the antiderivative. And then if I plug in 0, I'll get e to the 0 power. E to the 0 power is 1.
But it's still negative. I guess it doesn't matter if it's 0.
Yeah.
And we factored it out.
E raised to a real number power is never a negative number. Even if it's like e to the negative 5.
Oh.
That's just 1 divided by e to the positive 5, so it's just a small real number. And then e to the negative pi is not anything, so we just write e minus e to the negative pi. Just is what it is. And if you want to, you can box your answer, because that's as simple as we can write it, or you could punch it into your calculator and figure out what this is going to be. Square root of 2 times e to the pi, e to the negative pi, minus 1. That's weird, I'm getting a negative number. Oh, you're right. Because the lower bound's supposed to be negative pi, not pi. So make that a positive pi. And then we'll be good. 31.31. And we'll see, does this look like a 31.31 length curve? I think so. Looks like 24 in the x direction, plus it's got a lot of curvature to it. So yeah, I can see it being 31. Cool. Questions? No? All right, what is the length of the following polar curve? R equals theta for 0 to 2 pi. So R equals theta for 0 to 2 pi looks like this. Let's see what we get. The r squared part is going to be theta squared. Dr d theta is 1, so if I square that, it'll still be 1. Does everybody agree? So then what strategy do we use to solve this integral? Trig sub? All right. We see a variable squared plus a constant squared. And so trig sub would tell me, let's substitute u equals a times tangent theta. Except we're not going to use theta for our trig sub because we already have a theta variable. And so we're going to have to use pick out a different variable, like maybe phi. Symbols don't really matter. You can use whatever you want. But that way we'll write theta is equal to 1 times tangent phi. And when I draw my triangle, my trig subtriangle. This angle is going to be phi here. And the definition of tangent is opposite over adjacent. So the opposite side should be theta, and the adjacent side should be 1. And that way the hypotenuse has a length of theta squared plus 1 squared. Sorry, square root of theta squared plus 1 squared. And that way if I want to get my integrand, what trig function of phi would give me my integrand? Secant of phi is the square root of theta squared plus 1. So we might try to start writing my length integral, at least the antiderivative part, in terms of secant, right? Secant phi. But I need to figure out a way to convert the d theta into phi's, like a d phi. And so the derivative of theta with respect to phi is secant squared phi. So I can replace the d theta with secant squared phi d phi. And it's our old friend. The antiderivative of secant cubed. How crazy that it shows up in the length of y equals x squared, the parabola, and it shows up in the length of this spiral, the r equals theta spiral. And so just in case you forgot how to do this, let's go ahead and solve the problem. We do integration by parts, where we can take a derivative of secant, so that will be our u, and an antiderivative of secant squared. And the integration by parts formula goes u dv equals uv minus v du. So, du is going to be secant phi tangent phi d phi, and v is going to be tangent of phi. Do you remember what to do when we get to this point?
Convert the tangent squared into 1 minus secant squared.
That's right. Yep, because I always have to remind myself how that works, but like cosine plus sine is 1. So if I divide everything by cosine squared, we get tangent squared somewhere in there. And that means the tangent squared can be replaced by secant squared minus 1. And so we split this up into two integrals. The first one is the same as the one we started with, secant cube. And the next one is plus antiderivative of secant phi d phi. And I believe the antiderivative of secant is the natural log of secant plus tangent, I think, for that one. So you add L to both sides and then you divide both sides by 2. And that's where we pick up the 1/2. And this was actually a definite integral. I mean, that had a lower bound and an upper bound. This wasn't just an antiderivative. So at this point in the problem, we should go back and track down what my lower bound and upper bound were. In terms of theta, 0 and 2 pi were the lower bound and upper bound. But when we converted it from thetas to phis, I have to convert my lower bound and upper bound into phis and not thetas. So like, I could write phi equals arctangent of theta. And what is the arctangent of 0? And what is the arctangent of 2 pi? By the way, don't worry about the arctangent of 2 pi. That's not a number you should know. But what is the arctangent of 0? That might be a number you know. It's 0. Yeah, and if you didn't know for sure, I'll just show you the way I think about it. Because this is the tangent function. And if I just narrow it down to the principal branch of the tangent function, that's between negative pi over 2 and pi over 2. This is what it looks like. And then its inverse function, every inverse function is a mirror image over this diagonal line. So in green you've got tangent, in purple you've got arctangent. You can see it's a mirror image. Well, tangent of 0 is 0 because it's sine divided by cosine, and sine of 0 is 0. And then if the arctangent is a mirror image of the green function, and the green function passes through the origin, then that means the purple function has to pass through the origin as well. And that's what makes me think arctangent of 0 should be 0. But that means the lower bound gets to stay 0. The lower bound was 0 before when it was a theta, and now converting the theta to a phi, well, it's just converting 0 into arctangent of 0. Arctangent of 2 pi, I don't think that's like a number you need to know. I mean, if you were asked for like the arctangent of square root of 3, you might be able to answer that question, or the arctangent of 1, you might be able to answer that question. But arctangent of 2 pi is just a weird number. It is what it is. So that our upper bound is arctangent of 2 pi. And then we keep those lower and upper bounds all the way down to the end here, so that when we finally have our antiderivative, what we do is we plug in upper bound arctangent of 2 pi in for the phis, and then you also plug in 0 for the phis here, and we see what we get. What is secant of arctangent of 2 pi? I guess you could just plug it into your calculator. The other thing we could do is we could figure it out from our triangle. Like if we say that theta is equal to tangent of phi, then every time I see a tangent of phi, I could write theta. And this is my triangle. Secant of phi is, oh yeah, we already wrote that one down. Secant of phi is square root of theta squared plus 1. I write this because the upper bound in phi was arctangent of 2 pi, but the upper bound in theta was 2 pi.
So you can either change your upper and lower bound, or you can convert back to thetas.
Exactly. And I think it might be easier to convert back to thetas, actually. It might not be true in every case, but in this case, I feel like converting back to thetas might actually be helpful, because remember, secant of theta is the square root of, sorry, secant of phi is the square root of theta squared plus 1, and tangent of phi is theta. And so now let's plug in 2 pi and 0. And I'm going to do the whole thing with 2 pi first. All right, so this would be 1/2 square root of 4 pi squared plus 1 times 2 pi plus 1/2 natural log of square root 4 pi squared plus 1 plus 2 pi. And then we are going to subtract what we get when we plug in 0. And if I plug in theta is equal to 0, then the first term is 0. This is a 0. This is 0 squared plus 1. The square root of 1 is 1. What's the natural log of 1? 0. So when I plug in theta is equal to 0, everything goes to 0. And the only thing I need to put in my calculator then is this junk. The 2's cancel. At least then I get pi times square root of 4 pi squared plus 1 plus 1/2 natural log of 4 pi squared plus 1 plus 2 pi, and so forth. Okay, to the calculator. Square root of 4 times pi squared plus 1 is 6.362. 6.362. So let me do 2 times pi plus 6.362. That's 12.65, 12.65. Natural log of 12.65 is 2.54 divided by 2 plus pi times 6.362. 21.26 ish. Okay, so the question is, does our curve look like it's about 21 units long? Not that one. Man, I'm really bad at estimating this. I feel like it should be. Let's take an integral from 0 to 2 pi of square root x squared plus 1 dx. 21.26. 21.26. Yeah, that's it.